In the last class, we already discussed this problem, right? We already went through the idea of it, and we talked about how setting the bottom of the well as ground level would be a useful technique in this problem. Okay, the idea behind that is to recognize that if I call the bottom of the well ground level, now I know that this object is going to not only come to the top of the well, but all the way up an additional 3 meters up to this level up here. So the total vertical change in height was 28 meters. And a couple students even came after school yesterday at office hours to ask a little bit more about it. And I said, well, you could also just call the lip of the well ground level, and then this is a height of 3 meters, but this is still a vertical change of 25 meters. So whether you do it one way or the other, you'll get the same answer. Now, the rationale behind that is that if you want to find the change in the object's potential energy, we take the final potential energy minus the initial potential energy. So if you call this ground level, you're going to have some positive potential energy here minus a negative potential. And minus a negative really means to add to it, which is where the concept of 28 coming into play plays a role here. So again, I'm calling this ground level at the bottom. So it means that my initial potential energy is 0. It's really useful in physics to make your frame of reference help you solve the problem. If you make the bottom 0, it drops off that entire piece. You're going to see this again when we talk about torque. We're going to talk about rotational equilibrium and torque, like levers. And based on where you look at the rotation, it'll help you to alleviate or get rid of some of the forces playing a role in the problem. So that's why we do this in this setup. So when I look at this, I could say that my final potential energy is the mass times gravity times my final height. And that still is my change in potential. Because again, this is just minus off the 0 that we started with. There was no potential energy to start this problem. So this is simply a plug and chug at this point. Okay, if I want the change in potential energy, I take the mass times gravity times the overall final height with respect to my ground level, which is 28. We have a sum of 25 and 3. So my value for that is, what do we have here? Doesn't, Mr. Toro probably has it downstairs. If you could somehow get it before the end of this period, it'd be awesome. Yeah, thank you, Steve. Or figure out another way to do it. 10,987 joules. So here's what you're going to notice, by the way. The unit of a joule is actually a quite small unit. It's very small. So your answers look very large here. But it'd be like saying the distance traveled is 4,000 millimeters. 4,000 sounds like a big number, right? But relatively speaking, we know that a millimeter is a very small length compared to a macro scale like a human body. So in this case, this looks like a lot of energy actually. It's not that much energy. You can go ahead, if somebody wants to right now, maybe help me out. Convert this to calories. And you can type in kilocalories. So 10,987 joules to calories with a capital C. Lowercase c is actually a different form of calories, believe it or not, which is ridiculous today. Capital C for calories, or use the word kilocalories. I think the answer is only going to be like 25 calories or something like that. I think it's on the order of 25 or 250 or something like that. It's not a lot of calories that are needed to lift this object. What do you get? Yeah.
2,000.
So just move it 3 spots. Move the decimal 3 spots over.
Is
it just 2 point something?
Yeah, 2.626.
So it's about 2.6 calories. Yeah, so the way it works, listen carefully, lowercase c calories were the original introduction of the unit of heat in calories. And that's used in a lot of chemistry purposes. Now, the calorie that you know is a different version of that calorie that we're talking about in chemistry. We talk about that as a capital C. It's really a kilocalorie. It's 1,000 times what calories are defined as on a small scale. So when you talk about food calories, this is literally 2.6 calories. So that's how much energy you would burn from simply lifting an object. Now this object is pretty heavy though. 40 kilograms, that's about 100 pounds. So you're lifting a 100-pound object 28 meters by pulling down on a pulley, which raises it up. You're only burning 2.6 calories in the process, or using that much energy. Chris?
So like when you eat too many calories, then you have too much energy?
Yeah, so technically when you eat a lot of calories, they give you energy. If you you don't burn those calories by exercising, by moving a lot, you're gonna, that calories, that energy, that's what eventually turns to like fat in your body. Literally, that's what's happening. So the amount of food you intake in calories, that's why some people call them, have used the phrase calorie counters. Like if your parents sometimes, not trying to stereotype, but generally like a lot of people that are into their fitness when they get older are, not just young people, but older people also, are all about calorie counting. So they're like, oh, I ate 300 calories this morning. How much did I burn off later on? So the average caloric intake, if you look at your daily value, is 2,000 calories. That's what it says in the back of most labels. When it says the percentage of your daily value, it's based on a 2,000 calorie diet. Now, you guys are younger. You consume a lot more calories than 2,000 than you guys are not. And your metabolism is so much higher than when you're older. So it's not as necessary, but it is still recognizing that if you're taking a lot of calories and not exercising, you'll recognize that, over time you'll end up gaining weight physically. Now again, everybody's different, metabolism is different stuff, but that's the idea behind it. You'd be expending or burning 2.6 calories in this process. Let's take a look at this next example here. So we've got an example of an ant, right? And there's no numbers given here, we're noticing. We're not giving the ant's mass or anything. But we know that the ant has potential energy and it keeps changing it because it's walking up and down little anthills. Okay, so we think about it on a microscopic scale. Have you ever seen Honey, I Shrunk the Kids? Think about Honey, I Shrunk the Kids here when they're like really small. Those ants are scared. When I was a kid, it was really small. So think about an ant going up and down hills or traversing a backyard. A backyard for an ant is like a marathon, right? We got to consider that idea. So going up and down hills is like us climbing up and down mountains in a sense. Now, ants are a lot stronger, but that's one other story. At instant A, it's carrying 3.5 times its mass, in addition to its normal mass. This is normal for ants. They can carry up to like 600% of their body mass. It's incredible. It'd be like you lifting 900 pounds and just walking with it normally. Literally, if you weigh 150, 6 times that, 900 pounds, ants are really strong. So it's carrying 3.5 times its mass on its exoskeleton. It's at half the height that it is at instant B, where it's not carrying food. So currently at instant A, it's half the height that it is at instant B. At instant B, something happened to its food. It ate it or dropped the food along the way. Which instant does the ant have more potential energy, and by what factor? Now, it could be useful to use numbers if you want. You could give the mass of an ant a certain value, call it 1. And then the food it's carrying is 3.5 times that. But you don't need to use numbers here. This is one of those times where variables all work. And we talked about this in the other example. I said sometimes your mass cancels out. And you saw that yesterday with the sliding problem with socks. The mass dropped off on both sides. So let's continue to take this approach where we try to use variables a little bit more. And I'm slowly kind of like weaning you guys off of numbers and into variables because they're a little bit easier to work with here. And we'll see the cancellation. So if I think about a figure of this, here's the ant right here at location A. And then it's going to go up to location B. The reason I drew my levels what look like proportionally double is because it says at instant A, it's carrying 3.5 times its mass, and it is at half the height of that at instant B. So instant A is half the height of instant B. So I know that my diagram looks like this already. Do I know what those heights are? Am I given the values? No. But I know that one is double the other. Agreed? One is double the other. So instant A, I could call this 1/2 y. In instant B, I could call this just y. I don't know the value. If you want to put in a number, it's fine. Call this 10, call this 120, or call this 20, call this 40. It's up to you to decide which way you want to appropriate it here. But it doesn't matter what the numbers are. Now the mass we know, when it's at the top, so I'm going to put a box. I know it's not a box, but that's what I'm making it easier. So here's my ant at the 2 locations. When it's at the top, it's not carrying the food. It lost the food somewhere. But at level A, it is carrying food, and that food is 3.5 times its mass. So I'm going to put that on top of its back. There's the food. Okay, and I'm just drawing it larger because it's more massive. It's not physically going to necessarily look that way, but that's what we're saying, or we're visualizing. So I know that the mass of the ant here is m, and here's the mass of the ant there. But we just said that the food is an additional 3.5 times the mass of the ant. So this is my diagram right here. I've got the ant carrying food at half the height. I've got the ant by itself at double the height it started at. And the question becomes, which has a higher potential energy? So again, we don't have numbers. We don't have numbers. So what we should do is probably look at the values of potential energy, but in terms of all variables. So at location B, this is the easier version. At location B, and then at location A. At B, what is the potential energy based on my variables? Based on my variables. And what's my formula for potential energy to start all problems? My formula to start the problem for potential energy, Alex?
Mass times gravity times height.
Height, very good. Even though it's a y, we know that that's a height there. Very good. So that's my general formula. And look at location B. The mass is just m. The height is just y. And the gravitational constant is g. So it's just literally mgy. For the potential energy at location B, it's simply mgy. But at the other location, the height is not equal to y. The mass is not equal to m anymore. So I have to use the numbers here for location A to see how they differ. But location B is literally just mgy because we define the mass as m and we define the height as y. I did that on purpose so that this answer just looks like our normal formula. And in this one, we'll see what it changes to. So what's the mass in scenario A? The total mass.
3.5 m plus m.
Which is?
Which is the total mass.
Sum them together though, they're like terms.
4.5 m.
Yeah, 4.5 m. So Gigi's right to say it's m plus 3.5 m, but together that's just 4.5 m. What's my gravitational constant still at this point? It's still g. It's not going to change there. We're assuming it doesn't change with height, right? An anthill is maybe a couple millimeters higher than the ground, so it's not going to change with height. And then what is my actual height? Luce? Half of? Very good. And all she's doing is recognizing, hey, look at the diagram. It's half the height you start or half the height of B. So I'm going to use these values instead. So these look very similar. They both have mgy. You notice that? You notice that both have mgy? What does this coefficient become? If I take 4.5, remember, multiplication is associative and commutative. So I can drop all these parentheses. I can reorder this and put the 1/2 in front. Everybody understand what I'm saying there? Multiplication, I can change the order. So half of 4.5 is what value? What is half of 4.5? 2.25. So the potential energy at location A is 2.25 mgy, while the potential energy at location B is just mgy. Well, which is bigger? Is a number bigger or 2.25 times that number bigger? Just use logic. Yeah, 2.25 that number, assuming it's positive, obviously, which it is. Take any number that's positive and multiply by 2.25. It's bigger than the number you have there. So this must be a larger energy at location A than it is at location B. Even though location B is higher up, the ant lost the mass. The mass plays a role as well. Remember, it's mass and the height that really affect potential energy. We're assuming we're always on Earth. Gigi.
I'm just going to use where you got 2.25 from here.
I just did 4.5 and times 1/2, because those are my two numbers, right? And everything else is mgy. So I think of multiplying these two together, and half of 4.5 is 2.25. And then I just carry down my other variables. The idea behind this is I want to make these two answers look very similar, don't I? I want them to both have mgy, but this one has a coefficient. That coefficient, because it's greater than 1, tells me that this energy is more than this energy right here. Try numbers for m, try numbers for y, and you'll get answers for your amount of joules. And that's fine, you can do that, but I want you to see this. Now, the second part is really easy to solve because I did it this way. By what factor is the amount of energy larger at A than it is at B? What's the factor? 2.25. That's all it is. This is the factor of increase. Think about math and direct variation. If I take a value and put a 2.25 in front of it, this itself is the increase factor. Now, if I did this with all numbers, I'm not going to do it, but hypothetically if I did, and let's say I got a value for the potential energy at B, okay, it equals some number, and then I got another value for the potential energy at A, it equals another number. How would I figure out the factor of increase if I was using those numbers? Imagine I didn't do it with variables, okay? Let's imagine I picked the mass and picked the height, and for PEB and PEA, nice. We have numbers for those two values. How would I find the factor of increase? Mathematically, take a math class. This isn't really a science question at this point. It's a math question. How do I find the factor of increase between two numbers? If my weight, yeah, Dan. You just divide them. You take the larger and divide it by the smaller number. So look at the problem. If I want the factor of increase, I would take the larger value over the smaller value. And really, if I do that here, I'm going to get 2.25. I'm going to get 2.25, and I'll see that with the variables. Potential energy at A is 2.25 mgy. Potential energy at B is mgy. What happens to mgy over mgy?
They cancel out.
And what am I left with?
2.2.
Yeah, that's exactly it. Stop talking?
Yes. You know, it's like insult to injury.
That's all right. I've been that way my whole life. There's worse problems than that. Okay, so the mgy drops off here and here, and my factor of increase is simply 2.25. This is really important that you recognize this. This is right out of your math, focus guys. This is right out of your math class. Factor of increase is not by how much it goes up. A lot of you made mistakes on the lab. That's why I'm pointing this out. The lab talked about how much friction went up or down, and some people said it went up by a factor of 50. No, it went up by a value of 50 because it went up by 50 newtons or down by 50 newtons. But if it went from 50 newtons to 100 newtons, what's the factor of increase? From 50 to 100, what's the factor of increase? 2. How do you get from 50 to 100? By multiplying by 2. The added value or the increased value is 50. The factor of increase is always, again, a quotient, division of those two numbers. Whenever you want factor of increase, take the larger over the smaller. Larger over the smaller. All right, let's continue. Let's talk about now this last topic in this section called elastic energy. And I already mentioned what it is. It's a spring or a rubber band or a bungee cord or a lot of things. Tension in a cable, technically, it really does stretch the cable a little bit. When you have tension in a cable, there's a little bit of stretch to all things. Anything can be modeled as a spring. Anyhow, my formula for this is very similar to Hooke's law. Remember Hooke's law from earlier this year was this. Fs equals negative kx. That was Hooke's law. Now we're looking at the potential energy that's stored in the spring. That's stored in the spring. Some textbooks use the subscript E for elastic potential energy, or S for potential energy in a spring or stored. So if you see either of those, they're kind of interchangeable. So if you're like advocating for yourself and looking at Khan Academy and maybe doing extra work when you can here and there, if you see a different nomenclature, that's all right. It just means elastic. But the formula is the same. 1/2 kx squared. What's k again? What's k? The spring constant. How strong the spring is. Its rigidity. What's x in this problem? What do we get for x, Sid? It's kind of like displacement. How far the string is stretched or compressed. Either one, depending upon what's happening. It is very much like displacement. Yeah, it's like the displacement of the end of the spring. You can think of it that way. Okay, it's not an object, remember. It's the end of the spring that's being displaced. So my units are joules because I'm looking at energy. Alex.
Is K the same every time?
K is dependent upon the spring. K has a unit of newtons per meter. But if a spring is stronger, there's a higher K value. The spring in your pen is a very low K value. The spring in the shocks in a car or in your bike brakes, when your bike kind of oscillates a little bit, those are a higher K value. Okay, a spring like I talked about at Amtrak, where the Amtrak line goes to the end, that spring that's there is a very high K value. Because if it ran off the track and couldn't stop, it needs to hit something to push it back. So let's look at an example of this. I can model anything as a spring. A trampoline, a bed, a bungee cord, a rubber band. Any of these things can be springs as long as they have elasticity. Elasticity. That's why it's called elastic potential energy. So in this case, we're thinking about a spring that's compressed from its free length of 10 centimeters to a length of 4 centimeters. Notice in centimeters. We're told that the rigidity of the spring is 300 newtons per meter, and we want to know how much potential energy is stored in the spring itself. stored in the spring. So right away, I know that I have a differential of x here of 10 minus 4 units of centimeters, or 6 centimeters. And in meters, I'm going to put 0.006 meters. Why do I put that into meters right away? Well, look at my K value. It's newtons per meter. And just a fun fact, with Hooke's law, if your K value was newtons per centimeter, then your x could be in centimeters. With Hooke's law, that was okay. But not for this topic. When we're looking at potential energy stored in the spring, it has to be my standard fundamental units of meters. My K value is listed as 300 newtons per meter. So what kind of a problem is this? Just simply plug and chug. Go right through the problem. PE equals 1/2 kx squared. 1/2 300 times 0.06 squared. What do I get as a value for this? 0.54 joules. Okay, very, very, very low value. I mean, we just talked about how 10,000 joules, right, was only like 2.5 calories earlier. So think about this. Now, logically, go think about it. What's 10 centimeters? I mean, 10 centimeters is this right here. And it's compressing down to 4 centimeters. So A, it's not a lot of compression in X, which stores more energy. The bigger X is, and X is a squared value, the more energy you have. And then the K value of the spring is not very large either. Okay? Yeah?
When I did, I got 0.0054.
Because I wrote the wrong value for my length. Whoops. This should be 0.06, right? That's why. Sorry. Drop a 0. I apologize. Drop a 0 here. Somebody correct me next time. I don't mind. That should be 0.06 when it comes to the actual length. Okay. Yeah, I moved another 0, right? It looks like 1, 2... Yeah, it's centimeter, centi, hundredth. That's why I was thinking millimeters. Gigi, thank you. All right, good point. And that makes sense. You got 2 extra zeros in your answer, right? When you did, you said there were 2 extra zeros because I had 1 extra 0 and it was squared. When you square something that's a decimal, it's going to be the amplified effect of it. So instead of 1 0, you're getting 2 there, just like 10, same as powers of 10s. So a very small amount of energy is what we're going to see for this problem. Have some homework for this. Definitely practice this homework tonight. We're going to start right into section 6.3 now. Okay, we're going to jump right into section 6.3 for the remainder of the period. It looks like a lot of problems. Okay, it's not tough. You're calculating kinetic energy. You're using the word kinetic energy theory. You're calculating potential energy. So it's a lot of plug and chug type problems until we get to section 6.3. 6.3 and 6.4 are a little more elaborate in the problem types.
The 6.1 problem set, what is that?
The whole problem set is not due until the day before the test. Always, yeah. So normal homework for 6.1 was due, I think, yesterday. Homework for 6.1 was due, right?
Yeah.
Or today, I forget, one of those. Yeah, the problem set for 6.1, 2, 3, and 4 will all be due the day before the next test. We're going to cover the whole chapter for sure. Okay? All right. Let us jump right into 6.3.